Hello everyone! In this video we're going to be solving a fantastic equation, a famous problem that goes back to Goldbach and Euler. This problem also appeared in the book Selected Problems and Theorems from Elementary Mathematics. I'm going to be sharing the link down below. So let's get started. We have x to the power y equals y to the power x, and we're going to be looking for real solutions, not just integer solutions. And why did I say integers? Because obviously there is an obvious, hopefully, there's an obvious solution to this if you kind of check it out. If y equals x, definitely it's always going to work like 5 to the 5th power is equal to 5 to the 5th. But I'm talking about different x and y here. Even then, we have an integer solution, which we'll talk about later. Let me not spoil the surprise. So let's go ahead and start by solving this equation in a more general sense. Well, we use this technique a lot, and remember, in other equations, we also use this, replacing y with something, which is, super powerful, right? Substitution. And it's a technique also used with differential equations. It's a change of variables, basically. So it looks like the following: y equals kx. So simple, but super powerful. Let's go ahead and replace y with kx and see what happens. Of course, I'm talking about under certain conditions here, so we don't really violate any of the rules. So first of all, I'm going to be raising both sides to the power of 1 over x so that I can get rid of the x in the exponent. And that's going to give me x to the power k is equal to kx, which is fairly simple. Divide both sides by x, simple. You get x to the power k minus 1 is equal to k. So you can kind of think of k as a constant for now. It's kind of like a variable, but kind of like a constant as well. Sort of like a parameter maybe. Is probably the right word. But anyways, I'm trying to solve for x, right, first. So let's go ahead and raise both sides to the power of 1 over k minus 1. And that's going to give me x equals k to the power 1 over k minus 1. Obviously, this is a value for x. But notice that k cannot equal 1 because we already talked about it. K equals 1 is going to give you y equals x, which is a super obvious, a trivial case, yeah. So let's go ahead and find the y value from here. If x is equal to that, remember y is equal to kx. So if you replace x with this, k to the power 1 over k minus 1, obviously this just means k to the power 1. So when you multiply powers with the same base, you add the exponents. 1 plus 1 over k minus 1 is going to be k minus 1 plus 1 over k minus 1, which is equal to k over k minus 1. To keep a long story short, y is going to equal k to the power k over k minus 1. So this basically gives us the value of x and y in terms of a parameter k, which is cool. So let's go ahead and explore this a little bit by using some numerical values. For example, what happens if I replace k with, say, I don't know, maybe 3? Okay, let's go ahead and do that. K equals 3 gives us what? X equals 3 to the power 1 half, which can be written as square root of 3. And y equals 3 to the power 3 halves, which can be written as square root of 27, which can also be written as 3 root 3. So square root of 3 comma 3 root 3 basically satisfies this equation. And obviously x and y are interchangeable, so you can also switch them around. Okay, this is just one example. Obviously there are many more examples. There are infinitely many solutions in this sense, right? But notice that these are irrational solutions, right? Obviously. Okay. What is that supposed to mean? Well, it just means that they are not rational. And in order to be able to cover all the real numbers, we also need to talk about if there are any real solutions. So it's basically what Euler did. He proved that there are rational solutions. Okay, cool. So let's see how we can explore it. Obviously, in order for this to be rational, I want 1 over k minus 1 to be a nice fraction. What is that supposed to mean? Well, I want it to be, since k minus 1 appears in the denominator, I want this to be a fraction like m over n, where this is in the simplest form. So this is in the simplest form, so that it can't be simplified. Now here's what happens. Let me tell you, to keep a long story short, this gives us k minus 1 is equal to n over m, and from here you get k equals n over m plus m over m, which is n plus m over m. Okay, so we got the value of k and k minus 1, so we can just go ahead and evaluate k over k minus 1. It is going to equal, this divided by that. And obviously when you do that, the m is going to cancel out, and you're going to end up with n plus m over n. Okay? So that's my k over k minus 1 value, and this is the 1 over k minus 1. Why did I find those? Because remember, when we wrote x and y, we wrote them in terms of k. So let's go ahead and replace k with whatever that is, and then we're going to be getting our solutions in rational form, hopefully. Okay, now I'm going to go ahead and make the replacement. So x is going to equal, let me change colors here. X is equal to, let me write it here. Okay, cool. X is equal to m plus n over m, and then that's to the power m over n, because that's 1 over k minus 1. Remember that? It's this one. Okay, that's my x value, and then my y value is going to be pretty much the same base, but a different exponent. And guess what? The exponent is going to be m plus n over n, because we're adding, we're just writing it as k over k minus 1. In other words, we're multiplying it by k. Anyway, so these are my solutions, and m over n is a fraction in the simplest form. In order for this to work, and in order for us to get rational solutions, here n needs to equal 1. So basically, for n equals 1, we get rational solutions. Again, I'm keeping a long story short here because I don't want to keep this video too long. So now what happens if you replace n with 1? You get basically m plus 1 over m to the power m, and y equals m plus 1 over m to the power m plus 1. So those are going to give you as a parameter, m is a parameter here in this case, all the rational solutions. Now let's go ahead and see if we can find some rational solutions from here. For example, what happens if m is equal to 2, right? If m is equal to 2, then we get x equals 3 over 2 to the power 2, and y is equal to 3 over 2 to the power 3. And from here we get x equals 9/4 and y equals 27/8. Obviously, again, x and y can be switched around because this is completely symmetrical, so we can safely say that x equals 27/8 and y equals 9/4 is also going to work. As you see, these are rational solutions, and if you check them out, you'll see that it satisfies the equation x to the power y equals y to the power x. Now, on a final note, let's go ahead and talk about integer solutions. Are there any integer solutions? And yes, there are. Obviously, integers are rational numbers, and if you use this parameter and replace m with 1, okay, so if m is equal to 1, then from here you're going to be getting 2 over 1 to the power 1, which is 2, so x becomes 2, and y equals 2 over 1 to the power 2, which is 2 squared, which is 4. So x equals 2, y equals 4, or x equals 4, y equals 2 is going to be the integer solutions of this equation. In other words, we can safely say that 2 to the 4th power equals 4 to the 2nd power. But interestingly, there are no other integer pairs for which x and y are different, for which this is true. Unfortunately, or maybe fortunately, who knows, this is the only solution, and it's amazing. Well, this brings us to the end of this video. I hope you enjoyed it. Thank you for watching. I'll see you tomorrow with another video. But before that, don't forget to comment, like, and subscribe. And until tomorrow, be safe, take care, and bye-bye.